Our Indie Lab was about rotating objects and the minimum speed of rotation and angle of precession. So these are all the objects I used, so I thought you guys could look at them. Some of them are actual tops, and some of them are like just custom items. This is actually this is actually the launcher for that one.
And so we kind of divided this into two parts. The first part was trying to determine the minimum speed that an object can rotate before it falls over. And then part two, some objects have, instead of just rotating on a single axis, like straight up, they tilt like this and kind of rotate on two axes at the same time. And that's called the angle of precession. Is that right? Mm-hmm. Yeah. And so we wanted to investigate the angle of precession as angular speed decreased.
Our hypothesis for part one that was that the higher center of gravity of the object, the slower or the faster the minimum speed would be. So it would not be able to maintain rotation at slower speeds. So we have a variety of objects starting from like an extremely flat top to one that's about 4 centimeters center of gravity off the ground. And then for part two, our hypothesis was that the angular precession of a top would decrease as the top gets slower, as its angular speed decreases.
And so here's a picture of all the objects. And we used a high-speed camera to do video analysis in Logger Pro to find angular speed. And we had also we had to use really bright lights because the camera didn't pick up light as well as you increase the frame rate. We actually had to go up to 480 frames per second to be able to see the rotation. And we also marked a lot of the objects so we'd be able to tell when they rotated.
So this is the background. There's about 3 basic equations we use. So angular speed is change in angle over time, and angular momentum is angular speed times moment of inertia. And then with moment of inertia, I had estimated values for each of the different objects because they all have different moment of inertia equations. So this is diagrams of the objects and what axes they were rotating on. This is a picture of the marker cap from the video of its rotation. And this is a diagram that explains precession. So I thought I would do a diagram to kind of show you what's happening. So if this is the marker cap here, you have your force from gravity pointing like that, but then you have the angular momentum from the rotation because this marker cap is rotating along its own axis like this way, but it's also rotating along an axis this way about that point, so it's going around like this.
And there's a video of it.
Yeah, and so when the angular momentum is big enough that the y component of it is bigger than the y component of gravity, then the object will stay up. And so then as the object's speed decreases, its angular speed, the momentum will get smaller and the y component will decrease, and that's why this angle here, this is the angle of precession right here, it will decrease as time goes on. And then we got this picture from hyperphysics, which kind of explained precession. This is for like a normal top though. And the marker cap was just the most obvious of all of them to show precession. So we recorded videos of the objects and analyzed them with Logger Pro, mostly from the top, finding angular speed. And then with the marker cap, we had the video from the side to get the angle of precession.
And so we also recorded several other characteristics of the objects, like the mass, the height of the center of gravity, and moment of inertia and the radius, and we compared the minimum angular speed with each of those characteristics to try and find which one looks like it had a correlation. And here mass doesn't really have a correlation like we thought. This point and that point seem to be like outliers that some would like eliminate, but we purposely chose items that had a variety of characteristics to try and make sure we don't mislead our data or get misled by our data. And height is the same thing. There's one all the way over here and here, if you can't see from back there. It doesn't really have a correlation. And again, radius, even less of a correlation. Same thing with moment of inertia. And this is height of center of gravity versus angular speed. And so it's not that pretty, but we think there's a correlation. Yes?
Is that the critical angular speed, the one where it begins to fall or,
Yes.
or touches or something?
Yeah.
Yeah, okay.
Yeah, that's what we mean by minimum.
Okay.
So this is the graph of the angle of precession versus the angular speed of the marker cap. I actually should show you the video.
Smart ink.
Drag it to the top of the
Yeah,
screen.
Derek, put it up, put the top of the window up. Yeah, pull that up. Derek.
There we go.
Oh. Just pull it.
All the way.
You can't do it.
Pull it harder.
There you go.
Okay. I'm going to skip some into the video. So this is the video of the marker cap rotating. This is on a high-speed camera for 180 frames per second. So it's actually spinning pretty fast. And it's, as you can see, it's processing this way, but it's also rotating around its own axis. And then over time, so basically I put this into video analysis, and every 5 rotations of the precession rotation, I analyzed the angle. And I had to do a horizontal distance and a vertical distance and do find the angle with the tangent of those, because LogPro doesn't let you analyze an angle. So as you can tell, it's getting lower as it spins, and then eventually it will be laying flat.
Go to slideshow.
Okay, so it obviously was showing there was a positive correlation between the two. If you were thinking about this as over time with the object, it would start up here with a higher angular speed, and then the angular speed would decrease, and the angle of precession would also decrease. And as it gets slower, the angle of precession starts to decrease faster. So then that is a positive correlation between the two. And the fit on LogPro that fit it best was the inverse. So this is a over x squared plus b, which I didn't know how to linearize that, and I couldn't really figure it out. Because it's not just a normal inverse, and it's not, it wasn't like a log, natural log graph either. So I don't really know what this correlation means, except that it's a positive correlation that's getting less.
It is a parabola?
Well,
It's not a parabola.
It's a over x squared,
Right.
and it said inverse. So it's not a parabola. It's more like, see, I thought it was going to be a log graph,
Right.
like steeper and then leveling out, but it didn't really fit. Like, it's the basic trend, but it didn't really fit. And then this one fit really well.
Did you try a square root?
Yeah, that's cool.
Yeah, I mean, it's a square root, but it's like not. It's because it's 1 over x squared. It's not square root, but it's kind of square root.
We also don't really
It
have.
kind of looks like a square root.
What happens if you fit it with a square root?
Can
Did it
you
just-
do a square root on LibraPro? Well, I
Come on, neighbors.
I think because I tried a lot of them and this was the best fit, but it was definitely not as good as this one.
Well, I mean, we're stopping way before the x-axis is hitting 0, so it definitely is not a square root. It's shifted parabola way
Because
up there.
it'd be pretty impossible to get a top that could stay upright with a very tiny speed, like almost 0 speed. That would be really hard. And like even this one is pretty amazing. It's that little flat top that just has like a little stick coming out of it.
How'd you measure that?
You spin it with your fingers. We videotaped it from up top, and we kind of graphed every rotation, or we made a point every rotation, so we had like a period. And to get our minimum speed, there was like, on the log profile, it would be like constant going down, and then there would be a drastic drop, which is when the top hits the ground and the friction makes it slow down really fast. Because for some of them, like the flat top, you couldn't tell just from watching the video when it falls over. But then the graph would show that.
And so for part 1, we concluded that height of center of gravity is the only thing that had a strong correlation with minimum angular speed. And we don't really know the actual relationship because we couldn't find an equation to figure out one. And there also are probably other factors in combination with each other that we didn't take into account or couldn't think of. And to do this better in future, we could test more objects and have even greater variety of objects. We tried to, like that object, the skittle, the white one, has a high center of gravity, and we wanted to find one with a low, like that was tall and had a low center of gravity. So we tried to find a dreidel, but we couldn't get one.
And then for part 2, angle of precession did decrease as the spinning slowed, which was our hypothesis. We know that there's a positive correlation between angle of precession and angle of speed, but we don't know what the actual relationship is. And then the angle of precession happens because of the competing angular momentum and force of gravity vectors, which is the diagram I drew. And then we should just test different tops because we only had one that really drastically showed precession. Like some of these other ones showed precession, but you can get a good video of it. Mostly because they move around a lot, so it's hard to get from the side. The marker stays in the same place most of the time. So yeah.
Thank you. I don't think we'll have time for questions, but I just had one comment. If you could work with Harry to make custom tops that would scale and change just one of the parameters, you may be able to better investigate, because the problem was you choose tops and they've got all the parameters different, right? And so it's hard to pull out any particular effect.
Yeah.
Thanks, guys.
Our Indie Lab was about rotating objects and the minimum speed of rotation and angle of precession. So these are all the objects I used, so I thought you guys could look at them. Some of them are actual tops, and some of them are like just custom ones. This is actually.
And rotate before it falls over. And then part 2, some objects have, instead of just rotating on a single axis, like straight up, they tilt like this and kind of rotate on 2 axes at the same time. And that's called the angle of precession. Is that right? Yeah. And so we wanted to investigate the angle of precession as angular speed decreased.
Our hypothesis for part 1 was that the higher center of gravity of the object, the slower, or the faster the minimum speed would be. So it would not be able to maintain rotation at slower speeds. So we
Is this an organ?
This is actually the launcher for that one.
And so we kind of divided this into two parts. The first part was trying to determine the minimum speed that an object